things in the barn in the back and whatever. And he was fine, except he would wake up and start yowling and whatever at like 5:30 in the morning, and which wasn't enough to wake you up, but it was enough to keep you awake when you did wake up. And I am old enough that I wake up in the morning here and there and whatever else. And so I was mad at the stupid dog. And then I was especially mad because it was dawning on me that I was going to have to, we were going to have to do something different. And because of my age and my gender, it was going to have to be me that did it. So I'm going to have to wake up with the stupid dog, which it did. And it was much better. Although for some reason I didn't wake up to one of my alarms. And so there was a nice little turd present. But even with taking care of that, it was still better than it was. So it's not great, not ideal, but we're at least in a better way. All right, so we got a triangle. It looks like this one. Got a point at 0, 4. And we got another triangle that looks like that one. And we've got a point which is at 0, 8. Which question is this? Number 18 on 7, 6. And we've got this point at 0, 0 that they share. And we've got a point at 6, 0. And we want to know what this one is, right? Find the missing coordinate. So, what should we do? Feel a little bit like in this chapter, feel like it's, I don't know if y'all have ever watched the old cartoon Animaniacs. Animaniacs would have a side spin-off, which is kind of funny because Animaniacs is almost a spin-off to begin with, but they would have a side spin-off called Pinky and the Brain. And Pinky would ask the Brain, "What are we gonna do today?" And then he would say, "Oh, Pinky, we're going to do what we do every day. Try to take over the world." So, anyway, all that being said, when I asked what are we going to do on this problem in this chapter, I don't know. Pinky, we're going to do what we always do. Write a proportion. Wow, that was exciting. Almost a disaster. So, we should write a proportion. What's the proportion going to look like? I don't know. 6th graders. I only taught 6th grade once in my public school career, and it was funny. I actually quite enjoyed teaching 6th graders. They were fun. I was teaching computer stuffs at the time. And every day, like literally every day, I taught in kind of an outbuilding. And so they would come through this breezeway and come to my class. Every day, I would tell them, "No, go back to the door and walk to my classroom." Because every day they would run. It was funny. Okay, so what's the proportion going to look like? What? Oh. What am I going to put here? 8 sounds great. If I put 8 right there, what am I going to put right there? Sure. I guess. Yeah, that's fine. I was thinking of it a different way, but this will also work. There's always like 2 ways to write a proportion almost. Right? Because you can flip it actually there's like 4 ways to write a proportion and to get the same answer. You can flip it over, you can, anyway, whatever. What's going to go right here? Not 0. Not 0. Not 6. 6 doesn't go with the 8. Which one's going to go with the 8? How about the one we don't know? That's the big triangle, right? So X. And it literally is x, right? X-axis. What's going to go here? Not 0. 6. Now what? Cross multiply. 4 times x is 4x. What's 8 times 6? Yeah. My brain was saying you were a liar, but my brain was lying to me. Because 8 times 8 is 64. My brain was trying to say that 8 times 8 was 48, but that's a lie. So, what should we do now? Divide. What does x equal? 12. So the point then is 12, 0. There's your 0. He came back. Welcome back, 0. What other questions do we have on either lesson?
Was 18 a proof like with the columns, or is it just writing?
On the first, on 7.5?
Oh, yeah.
Yes.
Can we do that one?
Sure, we can. Yeah, always if it says do paragraph proof or a flow proof, yeah, always just want a 2-column proof. We only do proofs one way. There's a possibility, it's a very like open possibility right now. So like, don't go like write letters to the editor or nothing, but there's a possibility I go back to public school next year. Hofer's theorem 7.9. And if I do, and if I teach math when I go back, one of the saddest things if I have to teach geometry is I probably won't even be able to teach proofs. Because I don't get a choice. I have to follow the TEKS, and they change the TEKS, which I think is one of the dumbest changes they've made ever. We've missed the entire point of geometry, but you know, whatever. Okay, theorem 7.9. So what does theorem 7.9 say? Where is it? Oh, I must have missed it. Theorem 7.8. Oh, that's a proof for theorem 7.8. 7.9. There we go. So theorem 7.9 says, if two triangles are similar, so let's kind of get some pictures that we can work with. Actually, I'm not going to draw the ones I did because those are more annoying to draw. Let's do a slightly different versions. How about?
Can you just make any random shape?
Yep. Well, it has to be in this one triangles because the theorem is about triangles. So any random triangles, yes. Do A, B, C, and X, Y, Z. Okay, so let's see. If two triangles are similar, the lengths of the corresponding angle bisectors are proportional. So we need some angle bisectors on there. So what are we given? We are given that triangle ABC is similar to triangle XYZ. Where are we given it? We're given it because the theorem says if two triangles are similar, right? So that's part of the given, right? Then they're angle bisectors, so we're also given, we need some letters over here. Let's put a D right here and a L, why not? Okay, right there. L is probably a stupid letter because it looks like angles. Try again. How about M? That seems more reasonable. Okay. What did they use? They didn't use anything like the letters I picked. That's fine. We are given that AD, segment AD bisects angle CAB, right? And we're given that XY bisects angle ZXY, right? And we want to prove that, excuse me, that the angle bisectors are proportional to the lengths of the corresponding sides. Excuse me. So, we're wanting to say that, make sure we're LP to RT, let's see, L, yeah. Also be true to LK, right? They only wrote half of it. They only wrote half of it, so we'll only write half of it too. So we're trying to prove that AD to XM equals AB to XY. This theorem would also be true for, like this picture, that AD to XM would be equal to AC to XC as well, right? So you could do that. You could write that proportion. But since their example on their thing only said one of them, we'll say the same thing. Now, that's what we're trying to prove. These are what?
How did you figure out what you're trying to prove?
So, I will say two things about that. One, you would never have a prove theorem blank on a test, because that's too much trouble. It would always be prove this picture, right? Two, I just read through the theorem and kind of looked at the if-then statement and said, okay, what is the result of the theorem? The result of the theorem is that the things are proportional. And so everything else from the theorem would be given. Does that make sense, kind of? Okay. And that's yeah, easy peasy. Now, the not so easy peasy. Now we got to figure out what to do. What I always say with proofs is you want to look at starting with the given, and does the given tell me anything else? Which it does, almost always. What does it tell me? True, so all the sides of the big triangles are proportional, so we can write those proportionality statements, and we probably don't necessarily have to do them all, right? Because we don't care about CB or ZY, but we do care about AB and XY, right? Because that's what we wrote in our, if we're going to prove this. So AB to XY, we're probably going to have to get something. So let me start writing, and then let's ask some questions to get you to think through the next bit. So AB to something equals XY to something else, right? Little triangle over here, big triangle over there, right? You could also do AB to XY equals something to something, right? Equal the same thing, right? Little triangle to big triangle is little triangle to big triangle. We need to know what to put down here. We have two options, right? We could either say AC and XZ, so AC under AB, XZ under XY. We could say that. That would be fine. We could also do the one down here, right? So the CB, excuse me, the CB under the AB and the ZY under the XY. We could also write both of those proportions and do it. That's another thing that I like to encourage when doing proofs. Sometimes when you're not quite clear how to get to the finish line, sometimes adding extra stuff is a good way to go, and just throw stuff up there that you know is true. Eventually some of it might have been useless, but it's better to have too much than not enough. Okay? So we need to figure out which ones we want to do. So do we want to do CB or do we want to do AC? The bottom side or the top side? And why might we choose one or the other?
XMAD? Because it's closer to the actual proof.
So AD and XM, is that what you said? So I like where your head's at. However, we can't say that. We don't know nothing about that top side yet. Let's do something else first. Let's put a pin in this. Let me come back to this. Let's do something else first and see if this will help us kind of with a path. So let's do something else first, and let's put something in our brain a little bit. So we're trying to prove that a couple of segments are proportional, right? We're trying to prove that a couple of different segments are proportional. Excuse me. So in order to get the segments are proportional, if we can get the triangles are proportional, then we can say their sides are proportional, right? So we need triangles that have these things in them, AD and XM in them, right? So it can be this little triangle with this triangle or this triangle with this triangle, right? Those are our options, right? So that's where we need to go. That's kind of where the finish line is going to be. For saying that a couple triangles are similar, therefore their sides are proportional. That's where we're going to head eventually. So how can we say triangles are proportional? What tools do we have for that? We have a few different ways we can do it. What were they? That was a lesson or two ago, right? One of them was one of the answers to one of today's things. So go back a couple of places. I think it's in 7.3. I could be lying. Might be 7.2. I was right. I wasn't lying. This time. There are 3 ways to prove a triangle is similar. What are they? You didn't go back far enough. So now those are some additional ways. There are some ways that you can say you've got parallel lines, but there's a core 3 ways without other stuff, without other parallel things or whatever else. Now, you can use parallel segments to get you there. But even before that, because that's not going to apply here, right? We don't have 2 triangles that are parallel. And if we made them be parallel, because we just made the pictures up, right? If we made them be parallel, we would be proving something else, because then it would only work for parallel lines. We want to say that it always is true. Corresponding angles are congruent. How many of them? You went back too far this time. 7.3. Remember I said I wasn't lying. It's in 7.3. That's confusing. 2 angles. Angle-angle similarity. So if we could prove 2 angles was there, then we can get there. What's another way to prove that triangles are similar? Side, angle, side, and side, side, side. Now remember that this is similar, right? Not congruent. So when we say side, angle, side, the angles are congruent, but the two sides around them, they're proportional, right? So we can get that, we could get there. Or if we could get all three sides are proportional, then we could say that the triangles are similar, right? Those are our options for getting this going. Now, so back to where we were, saying we could say something different, right? We could say, what can we, so we were about to use this, and we're going to go back and we're going to do that, but let's use this given first. What does the fact that the angles are bisected mean? Not proportional. I know, that's almost always the answer in this chapter, but not on that question. What does bisect mean? If I bisected Gavin, not only would I be a murderer, but what would I have done specifically? I'd split him in half. Bisect means cut in half, which means that the sides are the same, right? All right, so this angle is congruent to that angle. Ooh, that might get us a little closer to side, angle, side, right? Might get us there. So that one's congruent to that one, and this one is congruent to this one. Okay. So let's say that angle CAD is congruent to angle BAD, and angle ZXM is congruent to angle YXM. Because definition of bisector. Okay. Now let's add all our similarity things that we were going to add. How do we do it? We're going to end up running out of time before we finish this, if I had to guess. What I will probably do, since y'all will need to leave, is go ahead and write it all out and send it out as a resource on Classroom so that you can see the whole answer. But we'll get as far as we can get before you have to leave. So all the stuff we were going to say, right? So AB to XY. Now let's go ahead and practice what we preach, and we'll go ahead and just show it all on there. Then we'll have it. AB to XY equals little triangle to big triangle. So CB to ZY. And actually, we can just write it out as a long proportional statement, right? It'll be the same thing. So what is the third one? We got CB, so AC to ZY, because definition of similar, right? Okay. That's potentially useful, but what now? What else could we say? Oh, you know, there's something else that would make it. Well, maybe. I don't know. Do we have to do both? Let's see. What do they do? What'd you say? Literally side, angle, side. Well, so remember that we're talking about the little triangles, right? We need the little triangles. This one and this one, or the other side, right? Not the big triangle, right? So if it was side angle side, we'd have to have this, this, and this. All we have is side angle right now, right? Side, and we don't really even have that. All we have is that these two are congruent and that they bisect. But we can grab some other angles. We can say that some other angles are congruent. What angles can we say are congruent? This is a weird proof, but I do want to get this one thing before we go, and then I'll write out the rest and let you leave. What angles can we say are congruent because ABC is similar to XYZ? Let me disappear all the stuff and make it even simpler. Make a couple other triangles. So, if I'm told that triangle MPN is similar to triangle, wow, that's definitely not similar, but close enough. Similar to triangle YLV. Why not? Who cares? YLV. What angles are congruent to what angles on this blue thing? V to N, that's true. Angle N is congruent to angle V. What else? M to Y and P to L. So, remembering this thought, what can we say is congruent over here? There isn't a V over here. Oh, B to Y. Yeah, true enough. Angle B is congruent to angle Y. We could also, don't know that we're going to need them both, we could also say angle C is congruent to angle Z, right? We could also say that angle CAB is congruent to angle ZXY. Why did I label these with just a single letter and these ones I grabbed 3 letters? Why did I change? Yeah, because there's 2 angles there. That's right. So you have to use the 3-letter. We could, this one could be named angle ABC. That's the same angle. But since there's only one, we don't have to write all of that. Because same as this, definition of similar. I'm going to keep writing. You can leave if you need to leave. The route the book goes is a bit interesting. And I didn't see it immediately either, so I would have had to think for a long time to get there. They say essentially this, but different. They say that angle BAD is 1/2 of angle BAC. should say consistent. I labeled this BAC and BA. Oh, just kidding. It's different. What am I saying? Yeah, no, I did it the same way both places. I'm just dumb. Okay. Anyway. It's half of BAC. What can we say for the other triangle? How would we write that for that one? What angle goes with BAD on the big triangle? YXM. Equals 1/2 of angle YXZ. Labeled it ZXY here. Let's do the same. Because of the definition of bisector, right? Bisector says it cuts it in half. What can we do now? I don't know that you've seen one where we had to do this yet. So this is probably good anyway. Even though this is kind of a weird proof of this bit. Because BAC equals ZXY, we can substitute this into there. I don't always draw the lines. Just like we do in algebra, right? If x equals y, then everywhere that y is, we can put an x instead. So we can say that angle BAD equals 1/2 of angle ZXY. It's about to be your favorite, Joe. It is going to be transitive in a minute. Let me write what I did here. I did substitution, right? This is 6. Substitution. So, since this equals this also equals the same, right? These two match. Transitive says that if A equals B and B equals C, then A equals C. So, transitive property, we can say that angle BAD, bad to the bone, is congruent, technically skipping a step, that's fine, to angle YXM, transitive property. So we said that this one is congruent to this one via the transitive property. So now we have angle, triangle ABD is similar to triangle XYM because of angle. And since they're similar, we can say that AD to XM equals, technically you should have measures on them, right? Measure of AB to the measure of XY. Because, let's do a CPCTC looking thing. Corresponding parts of similar triangles are proportional. You could write all that out if you felt like it, which you probably would, because it's not as easy to remember as CPCTC. How do you feel about it? This is uglier than a proof that would be on a test.
Yeah, I kind of don't want to see it again.
That's fair enough. This year I've got Algebra 2 right after, actually most years I have Algebra 2 right after this class. Sometimes I like to leave the proofs on the board, especially when they're ugly like this one, just to give them nice flashbacks.
I like the other proofs better.
Yeah, this one's pretty ugly. We technically didn't need some of the things that we put in there, but like this one, we never used this again. Did we use this? I don't remember. I don't know if we even used that ever again. I think we just used this from here down, but that's okay. More is fine. Not if we're professional mathematicians, though. If we're professional mathematicians and we're actually writing proofs like for real. All of these have already been written, so we don't have to write them. But if we were writing proofs for real and wanting to say that this is always true, then we would want to clean it up. But we're not professional mathematicians. Goodbye, kids.